the primitives and the computation of areas are strongly related with one another, okay? So it does two things. A bridge between differential and integral calculus, and a bridge between two very different problems, measuring areas and computing primitives of functions. So the definite integral is also called the Riemann integral. Okay? It's also called the Riemann integral, and is related to the problem, is originally related to the problem of measuring primitives. Okay? So assume that f of x is a function like this. This curve here. So it is bounded, I mean, it doesn't go to infinity at some point of this interval, okay? It's defined over an interval. It's very regular, but the point is that this area has, let's say, three sides that corresponds to straight lines, basically, okay? And one side is, in fact, a curve, okay? And we want to measure the area between the curve that represents the graph of the function and the horizontal axis. This is the problem. Limited to some interval, a, b. Clearly, if this function was a straight line, no problem to compute the area, because you can always reduce the computation of the area to some rectangles and some triangles, okay? But the point is that this is a curve. So how do we compute this area? Okay, this problem is strongly related to the search for primitives of a given function. So this is the problem. Initially, we assume that this curve is above the horizontal axis. Okay, it is above, but the same logic also applies to the cases where it is below the horizontal axis, or when it changes from above to below, okay? In the first elementary version, we consider a function which is non-negative over the interval, the given interval. The function must be very regular. Basically, what we require is that the function is continuous on this interval, and it is bounded. I mean, this just means that it is regular like this. It takes on finite values everywhere. It doesn't, for instance, have a limit here which is plus infinity on one side of the interval, okay? It doesn't have any vertical asymptote, basically. Okay. And the Riemann integral is based on a very old method of basically approximating this area by computing the areas of small rectangles, which is very intuitive, okay? You may know already this, but this is, I put this in the slides just for completeness, but you're not required to know this, but it is essential to understand the properties of integrals. So remembering the construction of the Riemann integral based on rectangles is essential, is important to remember some important properties of integrals, which otherwise might seem counterintuitive, okay? Okay, so what is the method? Divide the interval on the horizontal axis in n parts by choosing n division points, basically, okay? The first point is x0, which is the lower bound of the interval, then x1, x2, xn minus 1, and xn, which is the upper bound. So like this. Take the interval between a and b, put some intermediate points, so you divide this interval in a number of n smaller intervals, okay? And the idea is that for each interval, we construct a rectangle. And this is the base, for instance, of the first rectangle. What about the height of the rectangle? We take just one among the values, just one among the values that the function takes in this subinterval, and we take the height at that value of the function, then we build our rectangle. So basically what we do, we select a point in each of these intervals. For instance, for the first interval, we select point psi1, about in the middle. Our construction is independent. Our final result is independent on the way we select these points, okay? We select a point in the middle. Okay, what is the value of the function at this point? Is f of psi1. Take this level, draw this horizontal line here, and now we have a rectangle here, okay? The base of this rectangle is x1 minus x0, and the height of this rectangle is f of psi1, okay? We do the same for each sub-interval. For instance, for the second interval, the base is x2 minus x1, this segment, and I want to take, for instance, the point at the upper bound of the interval this time, okay? Because it is independent on my choice. So the height is here, okay? So I draw this upper side of the rectangle, and I have another rectangle. Then the third one, like this, and so on and so forth. So the important thing is that we divide the given interval into n sub-intervals, okay, by selecting some division points. For each sub-interval, we select a point in that sub-interval, maybe also at the boundary, not necessarily an inner point. And we define a height of that rectangle accordingly, and then we have a rough approximation of the area below the curve by a sequence of the sum of the areas of n rectangles, okay? And we can compute the areas of these rectangles and regard this as a very rough approximation of our area. So, for instance, the area of the first rectangle is x1 minus x0 times f of psi1. The second one is x2 minus x1 times f of psi2, and so on and so forth. Okay, so what is delta xi is a short notation for instance, x1 minus x0 is delta x1, x2 minus x1 is delta x2, etc. It's the length of the base of each rectangle. Okay, so we have identified intervals of amplitude delta xi. Each delta xi is 1 point minus the previous one, minus xi minus 1. And we have a subdivision of our interval. This kind of subdivision is called partition, mathematically, a partition of our initial interval. So what is our rough approximation of the area? It is this one. So the area of the collection of rectangles is the approximation of the area f of psi1 times delta x1 plus f of psi2 times delta x2, etc., plus f of psi-n times delta xn. Short notation, which is important here because this is the notation that then originates the corresponding notation for the integral, okay? Because the sign of integral is a sum, basically, okay? So we have the sum of the area of each interval of each rectangle. The area of each rectangle, and this is the counter that runs from the first rectangle to the nth rectangle. Okay. This is the area of the collection of rectangles, and this is called a Riemann sum, one among the infinitely many Riemann sums associated with our function over the given interval. We can build infinitely many Riemann sums because the Riemann sum depends, for a given function and a given interval, a Riemann sum depends on the subdivision that we select first, and then on the points that we select within each sub-interval, okay? So given the same function and given the same initial interval a, b, we can build infinitely many Riemann sums, so we get infinitely many possible different values of the area, depending on our subdivision, where we select points x1, x2, xn, and how many points we select, and the points psi I within each subinterval, the points that determine the height of the rectangles, okay? So it's totally, I would say, it's totally subjective, okay, the area. But there is an important point here. First, suppose that something happens, and this suppose happens in most cases. It happens when function f is sufficiently regular, okay? Suppose that as n tends to plus infinity, as we select more and more points for the subdivision, okay? And simultaneously, the largest among the intervals tends to 0, so we have to select many more and more points. And accordingly, the length of each small interval must reduce in size, okay, and tend to 0. The Riemann sum admits a limit, has a limit, okay, converges to some common value which is independent on the way we do that, on the way we increase the number of subdivisions, on the way we select the points, okay? The important thing is that we select more and more points and the length of these intervals tends to 0. Then we say that f, our function, is integrable. So this is the meaning of function integrable. A function is integrable when we are able to arrive at a unique limit by this process, okay? And more precisely, the function is called Riemann integrable just because there are many different definitions of integrability, depending on different classes of functions. Then, if this happens, we say that our function is Riemann integrable over the initial interval, and we have a limit. Okay, this limit is called A, capital A, for instance, which is the limit of the Riemann sum as the number of points tends to infinity and the length of the intervals tends to 0, accordingly, of the previous sum of rectangles. And this limit, if it exists, is indicated in this way. You see that the sign of a stylized sign of summation, which is the sign of the integral. It's called definite integral between a and b of f of x dx. Okay? Where a and b are named lower and upper limits of integration. So this is the conceptual definition of a definite integral between a and b of a function, and accordingly we have a definition of a function which is integrable over some interval. Basically, if the function is sufficiently regular, which means continuous and doesn't have vertical asymptotes, if it is continuous, basically, over some interval, we are able to arrive at a unique limit by this process of convergence of the Riemann sums, okay? This approximation with rectangles, provided that we take a high number of rectangles with smaller and smaller bases. This also means that if we take a sufficient number of rectangles and a sufficiently small basis for each one, we have a very good approximation of the area, okay? This is intrinsic in the concept of a limit. If there is a limit, we don't need to arrive at the limit, okay? If we stay close enough to the situation that defines the limit, we have a very good approximation, okay? Is that clear? But the function must be regular, otherwise we don't arrive at this approximation. Regular means continuous, without jumps, basically, without jumps. In this case, we have this very important property. Okay, so this is just the mathematics. Now there is a first, not difficult, but important geometric point to understand. What about a non-positive function f? I mean, in this case, in this example, with this function, we would get an area, we would get an integral, so the limit of the Riemann sums, which is a positive value, okay? Because it is, I mean, this function is positive. the base of the rectangles is made of positive quantities. Base times 8 is a positive, okay? Positive times positive. And the area is, and the integral is positive. But what about a negative function? Imagine that we do the same with this function. We want to measure this area, and we try to measure it with the limit of the Riemann sums, okay? With the integral, definite integral. What about the areas of these rectangles constructed in the previous way? A positive base times a negative height. So that would be negative. If we compute the integral, in this case, this would be negative. So here we must be careful. If you want to compute the integral, in this case, we get a negative number because our rectangles have delta xi, which is positive, but f of xi is negative in this case, okay? And this is a negative integral. But, of course, you want to measure the area. The area of a region in the plane is by definition a positive quantity, okay? If you want to measure the area, we have to take the negative of the integral, or the modulus of the integral, okay? So be careful. In this case, both the integral and the area are the same thing, and they are both positive. In this case, the integral is negative, but if we want to measure the area, we have to change its sign and make it become a positive quantity, okay? So we have to take the modulus of the integral. Why is that? Because if you remember the construction of the integral, each term of the sum, f of xi times delta xi, is negative, because this is positive, but this is negative. Okay? So the integral defined as above is negative, but the corresponding area is positive. And the last step to understand this basic idea geometrically is about functions that possibly change their sign over the interval. Consider this function. It's regular, it's continuous, but it changes a sign over this interval. Okay? Now, imagine that you compute the integral. That is, you compute basically the Riemann sum with the rectangles, okay? You start to sum these small rectangles. You get something positive, positive, that increases positive because I add another rectangle, positive, and larger because I add another rectangle. Up to this point, I'm adding positive quantities, okay? But now, from this point on, I start to subtract quantities. So I'm going to reduce the previous accumulated value, okay? Negative, negative, negative. I add negative quantities up to this point. Then I start again to add positive quantities. So at the end, the value of the integral may be positive or negative. If you look at this picture, probably the value of the integral from A to B, between A and B, is some positive quantity because, let's say, this area plus this area is larger than this area, okay? Probably the balance is positive at the end. If we compute the integral between A and B of this function, we don't get an area, we don't have an area. We have, the mean is a balance among areas corresponding to intervals in which the function has different signs, okay? So basically the numerical value that we get for the integral is the sum of the areas where f is positive minus the sum of the areas where f is negative. Is that clear? But if we want to measure the corresponding area, which is defined by A1 plus A2 plus A3, all positive quantities, we have to split the integral into three parts, from A to C1, then from C1 to C2, then from C2 to B, and the first one from A to C1 corresponds to area A1, is taken with a positive sign. And the same happens for the third one. But the second one, in which the function is negative, would have a negative integral over that subinterval, and we have to change its sign if we want to compute the whole area, okay, of the region. So this is the most important thing. When you have the integral of a function that changes its sign, it may even happen that the integral is 0 at the end. Here is a very simple example, graphical example, that may clarify things. Oh my God, this is again yesterday's stuff. I want to show you two things. The first is a graphical case where it is plausible to guess that at the end our integral will be 0. This is A, this is B. If I have a function like this is for instance symmetric with respect to this midpoint of the interval, like this. Probably, I mean, this is just a graphical sketch, but the integral between A and B of f of x dx is equal to 0. That's clear because we have two different areas here. The integral from this point to this point is positive. The integral from this point to the final point is negative, and the two will be graphically more or less the same, okay? So the balance is 0. But of course, the area, suppose that this is perfectly symmetric, so this area is equal to this one, okay? So the area is basically given by the integral between A and C f of x dx minus the integral between C and B of f of x dx, or ideally, since the two areas are equal, it's twice the integral between A and C, f of x dx, okay? The integral is 0, the area is twice as much the first part, okay? So this is the basic idea. And the basic difference between integral and area. But of course, the areas, the problem of definite integral arises historically from computation of areas of plane regions, okay? Okay, oh, there is another thing I want to show you. Now, suppose, okay, let's do that later. This when we talk about the variable upper limit of integration, okay? Now, okay, I called A the definite integral when it is perfectly represented by an area. In general, it is not an area, it is a balance between areas. So in general, I call it R, okay? Stands for Riemann, okay? R is basically a balance of positive and negative areas. If the function is positive, our R is just A, it's just the area, okay? If the function is negative, it is just the negative of the area. If it changes sign, I generically denote it by R, it is a balance between positive and negative areas. Okay? And another thing that you have to understand, this is only notational, is that the variable x here is just a dummy variable. So it's not important how you call this variable, okay? Because this variable only runs between A and B, but it doesn't affect the result, of course. It doesn't appear in the result, so you can call it x, t, u, any number, okay? Any character. So what are the properties of the definite integral that follow directly from its geometric original idea? Construction based on the Riemann sum. And an important remark, preliminary remark, but this is really important, is that when we write the integral between a and b of f of x dx, we want to extend its meaning, and we want to allow also for cases where b, the upper limit of integration, is equal to a. Okay, so basically the length of the interval is 0 in this case. And we want also to extend it to the case where b is lower than a. Okay? So for instance, we want to give a meaning also to integrals like this. Okay? And also to integrals like this. In this case, b is less than a. So what is the meaning of this? Suppose that f of x, this is 1, and this is 3. It's not difficult to understand what the meaning is. Suppose that f of x is like this. And we want to compute the integral between 3 and 1 of f of x dx. Okay, so what we get here as the area is the integral between 1 and 3 of f of x dx, okay? What about the integral between 3 and 1? The function is positive, so the height of each rectangle is positive, okay? But if we do that, this just means that based on the Riemann sums, we start the subdivision from the upper limit of integration, not from here. This is not x0, x1, x2, and so on. We start here. This is x0, then we select x1, then we select x2, and so on and so forth, okay? And this means that the base of these rectangles is measured, remember delta xi is xi minus xi minus 1, okay? So x1 minus x0 is a negative number. x2 minus x1 is a negative number. So we are building a Riemann sum with positive heights of the rectangles, but negative bases. So we have the same numerical value, but with a negative sign, okay? So the property is that when we define this, this is just equal to minus the integral between 1 and 3 of f of x dx. We have the same numerical value at the end, but with a negative sign, with the opposite sign, Because if the function is negative, that would be negative, and that would be positive, okay? Clear? So we give a meaning also to this notation. So the integral, this is an important property. The integral between a and a of f of x dx is 0, clearly. There is no interval, okay? It's just a point, so there is no rectangles. There's a 0 measure as an area. And the integral between a and b is minus the integral between b and a, of the same function, of course. And then there is an important additivity property. The integral between a and b, we've seen this already in the previous example with the function that changes sign, but this is stated in general. The integral between a and b of f of x dx plus the integral between b and c of f of x dx, you add basically the computation of the rectangles over two areas, two intervals, from a to b and then from b to c, and what you get is the total area, or balance between areas, between a and c of f of x dx, okay? So this is additivity property with respect to the intervals of integration. Look at this example. And this is since we have also property 2, this additivity property holds in very general cases. So we don't really need to have this sequence of points A, then B, then C. I mean, B is larger than A, and then C is larger than B. We may have any order between these points, and we have a property that between B and C, which is exactly the property stated here. But what about this situation? The property is again this one, but the order of the points is not A, B, C, like in the intuitive case, it is A, C, B. But the property holds anyway, because take the area between A and B. What is the meaning of the area between A and B? It's the whole area, okay? Between A and B. Plus the area between B and C. What is the meaning of area between B and C? Now, B is larger than C, okay? So it's the negative of this area. So the total area plus the negative of this area, which means the total area minus the red area, is the blue area. But the blue area is again the integral between A and C of f of x dx, okay? So this property is very general, doesn't only hold in the basic case where the sequence of points is A, B, C, the ordering of points is A, B, C, but it holds also for any other possible ordering of the points, okay? So these properties, we can just learn these properties, but if you want to get the intuition of these properties, and then I run forward from A to B and then backward from B to C, and the final result is from A to C, okay? And this is the main problem. Okay, now we understand everything about definite integrals, their geometric meaning, their Riemann sums, but of course, except in very simple cases, it's not very easy to compute the area. Of course, this is not the usual way to compute these areas, because fortunately we have the fundamental theorem of calculus. So what is the main problem? How do we compute the area between A and B of f of x dx? We know its properties. How do we compute it? We have the fundamental theorem of calculus, okay? And also later in the solution of differential equations, and when modeling dynamics of some flow that accumulates over time, okay? So this is really an important concept. Look at this function. We have, everything is already here, so you don't need to write what I'm going to write now. I have a function that, for simplicity, it is defined everywhere, okay? For the whole real line, over the whole real line. X, f of x. This is y equal to f of x. We select an initial point, A. We know, for simplicity, I take a positive function, but what I'm going to say applies to negative functions, changing functions, and whatever. I already know what is the meaning of the integral between A and B of f of x dx. The integral between A and B of f of x dx is a number that, in this particular case, expresses the size of this area, okay? Now the point is, what is the meaning of this quantity? Here I take a variable upper limit of integration. I call it x, because it is variable. I could take it a little bit on the right, a little bit on the left, or make it change, okay? So what is the meaning of this quantity? The area from A to a variable upper limit of integration, x, defined in this way, r of x equal to the integral between A and x of f of u, du, t, dt. I can't call the running index, the running variable x, because x is the variable upper limit of integration. So usually we use t, but we could use u, r of f of t dt. Okay? So what is the geometric meaning of this quantity? It's the area between the graph of the curve and the horizontal axis, in this case, okay, from point A to point x, where x is a variable point. So it's a definite integral in which we have a variable upper limit of integration. Okay? Is that clear what is the meaning of, is it clear what is the meaning of this integral between a and x? Just a definite integral. The only difference is that the upper limit of integration is not fixed at b, it can change. I regard this as a changing quantity. What happens in this particular example if I change the upper limit of integration? Clearly, in this example, if I increase the upper limit of integration, I have this that increases. Is that intuitive enough? It increases because it is the area between a and x. If I move x to the right, I have a larger area, okay? So it increases. If I move x to the left, this quantity decreases because the initial point is fixed and I change the upper limit of integration. So I change the end of the interval where I compute the positive area. So what is interesting is studying the behavior of this function for changing x. And the fundamental theorem of calculus states two important things. And the important thing stated by the fundamental theorem of calculus is this one. It has two parts, the statement. Part one states that r of x, this function regarded as the area between a and x for variable x. R of x is a primitive of f of x. And this is the most important part of the statement, of course. What is the meaning of this? The derivative of r of x with respect to x, the derivative of this function, when I change the upper limit of integration, is exactly equal to f of x. Or if you like, the derivative is just the limit of the Newton's quotient, okay? So the limit as delta x tends to 0 of r of x plus delta x minus r of x over delta x, which is the definition of derivative, is equal to f of x. And the second part of the statement that follows directly from the first and most important part, if I want to compute the integral between a and b of f of x dx, I can do that very easily in this way. Take any primitive of f, any, not necessarily this one, because this is a primitive. We know from point 1. Take any primitive, this one or any other, of f of x. Compute the primitive at the upper limit b. Compute the primitive at the lower limit a. Compute the difference. And this is the value of the integral. Okay? This difference between the values of the primitive at the upper and lower limit of integration is also denoted in this way. So when you find this notation, this just means f of b minus f of a, or also this without the left vertical line. Different possible notations for this, okay? Where capital F is any primitive of f of x. Okay, so I don't prove this theorem, but it is very intuitive. So basically the first important result sets a bridge between the differential calculus and the integral calculus. Okay, and also it explains that a definite integral, an area basically, is a primitive of the function f of x at the upper limit of integration. Okay? So basically, you should interpret this in this way. Go back to this. Okay. Now interpret this x as time, call this u. u du, because I want to use t as the variable in the abscissa. This is just an interpretation. I mean, it's not really important. Just to bridge already this with the dynamics. This is variable t. T is the upper limit of integration, and this is a function expressed in terms of the upper limit of integration t. So this is f of t. Okay. F of t also here. Basically, the meaning of the fundamental theorem of calculus is this one. Here there is some quantity and it flows from time 0 to time t at a given rate. It flows at a given rate. You can, from applied sciences, a flow of water, okay, with a changing intensity. Here there is a flow of water with a low intensity, but the intensity increases, okay? It's a flow, it's the amount per unit time, and it increases over time, okay, in this example. A flow of utilities, a flow of profits, a flow of revenues modeled continuously in economics, okay? This is the flow level at time t. And what you get here is the accumulated value from the initial time a up to time t. And the fundamental theorem of calculus just says that the derivative at time t, the derivative of the accumulated value at time t is exactly equal to the flow, okay? So what is the marginal change? What is the marginal change of the accumulated value from time t to just 1 second after? It is the flow in that second. This is the meaning, okay? Is that clear? So basically, the fundamental theorem of calculus says that the derivative of the accumulated value is the flow at the terminal, at the time t, the end point of this interval, which is very intuitive because the accumulated value is the sum of the flow over the whole life of this process, okay? So the derivative, so the marginal change of the accumulated value in 1 second, in 1 minute, is just the flow in that minute, intuitively. So this is the meaning of the fundamental theorem of calculus, just already applied to future problems in dynamic analysis, okay? So basically here there is everything. If you like, in these slides, if you are interested, there is also the proof. There is a very nice way to visualize the Newton's quotient. So basically, the change of function r from x to x plus delta x is this blue area, okay? This is the change of function r from x to x plus delta x. This blue area is approximately similar to a rectangle. If you divide it by delta x, if you compute the Newton's quotient, which is basically the derivative, okay, you divide the area of a rectangle by its base. So you get the height, okay? And the height is this one. Clearly, the height here, f of x, is the derivative of function r of x at the point x. Okay, so this is the basic idea. It can be proven in many different ways. Here is based on the maximum and the minimum of the function over that small interval, but there are other ways exploiting the properties of the mean value theorem for integral calculus and other theoretical results about integral calculus, but I want you to get the intuition. So the main result is that r of x is an antiderivative of f of x. And what is really important here is the last page of these slides. So what is really important here is the proof of point 2 of the fundamental theorem of calculus. R of x, so the area between a and x, is point 1 of the fundamental theorem of calculus, is an antiderivative of f of x. So its derivative is f of x. Since it is an antiderivative of f of x, can be written as capital F of x plus c, where capital F of x is any primitive of f of x, okay? You know that a primitive can be written as another primitive plus a constant. So this is very intuitive. Now, what is R of A? So what is the value of function R, the area between A and X? If I take X equal to A, if you look at I compute the area from A to A, it's 0. So R of A, this one, we know it is equal to 0. Since R of A is equal to 0 and R of A is, F is any other primitive, is F of A plus C, this is 0. So our C is minus F of A. So what is C here in this equality? C is minus the value of this primitive capital F at the point A. So R of x can be written as F of x minus F of A. Okay? Now, when x is equal to B, what is R of B? Put B here is F of B minus F of A. But what is the geometric meaning of R of B? Is the area between A and B. Okay? But the area between A and B is our definite integral between A and B of F of x dx, which is equal to capital F of B minus capital F of A. Okay? So basically what the second point states is that you don't need to select a specific primitive. You don't need to select R of x, okay? Or any other primitive. You can take any primitive, compute it at the upper limit of integration, at the lower limit of integration, and then you get the value of your integral. And this comes from here, because R of x is any other primitive plus c. And from these logical steps, we arrive at this. And the important thing is that, would you like to try with another primitive? Don't take f. Take another primitive g, which is f plus a constant. Now, don't evaluate f at a and b. Evaluate g at a and b. G is f plus k. When I evaluate g at b, I have f of b plus k. When I evaluate g at a, I have f of a plus k. But the plus k and minus k can be simplified away with one another, okay? Just because you are evaluating the primitive at the upper point and the lower point, and the constant appears in both with different sign, okay? So the constant is always simplified away, and you are left with f of b minus f of a again, okay? So this is basically the idea of the fundamental theorem of calculus. Now look at this example. So basically now we have a very powerful tool to compute derivatives. It's enough that we are able to compute the antiderivatives of a function. We select one, possibly the easiest one. We evaluate this at the upper limit of integration, the lower limit of integration, and we compute the integral, okay? Let me show you a first example first, this one. Suppose that you want to, this is a very typical type of exercise that you may find in the examination about integrals, okay? If it comes to compute a definite integral, I usually use simple integrals, elementary integrals, okay? But please be careful. Never forget the geometric meaning of the definite integral, okay? This is also useful to check the final result, for instance. What about the integral between 0 and 5 of this function? 1 over 2 times 1 plus 0.2t dt. Here I use the t as a variable. I mean, this is just a name of the variable, but it could be interpreted as time, okay? So basically, our function is like this. Always try to figure out what is the behavior of the integrand, the function to be integrated. And in this case, it is like this. It starts from 1/2 and it decreases like this, okay? So this is f of t equal to 1 over 2 times 1 plus 0.2 t, which is 1/2 times 1 over 1 plus 1 over 5t, okay? It is this function. 0, we are interested in what happens between 0 and 5. Of course, I'm using different scales for the two axes. So we are interested in this area. So as a minimum, you expect that your result is a positive number, okay? Okay, let's compute the integral. First of all, we exploit the fundamental theorem of calculus. We want to find out over 1 plus 0.2t. Now, we have, which is 1 plus 1 over 5t in the denominator. Now we have an expression, which is a linear expression in t in the denominator and 1 in the numerator. If in the numerator we have the derivative of the denominator, which is 1 over 5, then this would be the derivative of the log of the denominator, okay? So let's put 1 over 5 here. So we are dividing by 5, and then accordingly we multiply by 5 here. So we have 5 over 2 log of 1 plus 1 over 5t plus a constant. Okay? This is our primitive of this function. Of course, you can always check your result by computing the derivative. Now, our integral, which is, in this case, it is an area, or the accumulated value of a flow, if you like, over time, from time 0 to time 5, is like this. It's 5 over 2. Remember that when you have a constant that multiplies your result, this constant, when you compute the difference here, you know, this is a notation for a difference, okay? It's this quantity evaluated at t equal to 5 minus this quantity evaluated at t equal to 0, okay? So this difference has a common factor, which is 5 over 2 in both terms of the difference. So this can be brought outside this operation, okay? So it's a multiplicative factor for the result. And then we can just evaluate this quantity at 5 and 0. What is the value at 5? It's log of 1 plus 5 over 5 is 1. It's the log of 2. And at 0, it is the log of 1, which is 0. So it is 5 over 2 times the log of 2. Well, the value of this area is 5 over 2 times the log of 2. I don't have here any scientific calculator, but there are many ways to check your results, okay? So the function is like this. You want to have a rough idea whether your result is at least plausible, okay? First, it must be positive, because it is the area of a positive function. Next, it must be less than 2.5, which is the area of this rectangle, okay? 5 divided by 2. 5 times 1/2. Because it is a decreasing function, which starts at 1/2, and then it decreases to 0, okay? So it must be between these two values, okay? Of course, this is, I mean, you're not granted that if this is satisfied, you have the right result, but it is a kind of control that you can perform at the end about whether it is plausible or not. So always try to guess like a bound in which your solution must be an interval. In general, using rectangles, we always have a rough idea of whether our result is correct or not. Is reasonable, at least reasonable. Now, compute this integral, given the same function. What is now the integral between 0 and t of 1 over 2 times 1 plus 0.2 u du? We are doing the same thing, exactly the same thing, but now the upper limit of integration is not 5, it is t, okay? So it can be here, for instance, or it can be here. It depends, it can change. The computation is exactly the same as above, up to the point of determining the primitive, of course, and up to putting the primitive into the lower and upper bound operation. So basically we have the same primitive as above, which is, it is here, it is 5 over 2 log of 1 plus 1/2 u. We have to change the name of the variable here because t will appear here now, okay? So it's 5 over 2 times the log of, it was 1 plus 1 over 5 u, evaluated between 0 and t, okay? So it is equal to 5 over 2. At the lower bound, it is the same. It is again 0, because log of 1 is 0. So what really happens here, what is really important is to put log of 1 plus 0.2 t. Okay? This is the result. How would you check your result? This is r of t, right? By definition of our r integral function, r of x. This is r of t. The integral between 0 and t of our integrand. This is r of t. R of t is a primitive of the integrand, so it is a primitive of this one. Okay? So its derivative must be equal to this one by the fundamental theorem of calculus. So we want to verify our result. R prime of t is equal to, here, 5 over 2 times 1 over 1 plus 1 over 5t times 1 over 5, okay? Equal to 1 over 2, 1 plus 1 over 5t, which is exactly equal to f of t. Is that clear? By the fundamental theorem of calculus, the area that we have computed with a variable upper limit of integration is a primitive of the integrand, f of t. If you want to check our result, we just have to compute the derivative of our integral. And we get this result. But by the way, we found r of t equal to 5 over 2 log of 1 plus 1 over 5t. But we found that the indefinite integral of our f of t dt, in the previous step, was equal to what? It was equal to, where was the indefinite integral? It was here. This one, 5 over 2 log 1 plus 1 over 5t plus c. Okay? So it's clear that our result is a primitive as well. So our indefinite integral was this one. We found this. Okay, so our r of t is actually belongs to this family, okay? It belongs to these families with precisely with C equal to 0, okay? C equal to 0 is due to the fact that we start basically from time 0, where our function, our primitive has a value of 0, okay? So this is basically the reason, but the important message is that our area, as stated by the fundamental theorem of calculus, belongs to the family of the primitives of the integral. Okay. Now, of course, there are other cases in which we can realize by examples that our area with a variable upper limit of integration is in fact a primitive of our integrand, okay? Now, there are some cases. I suggest you to have a look at these two examples. There are some cases in which we can realize very immediately that the rule to compute the integral, the definite integral, established by the fundamental theorem of calculus is the correct one, okay? There are two simple cases. One is the example in which our function is constant. For instance, f of x equal to 2. F of x is a function which is constant. For instance, equal to 2. Here we have k more generally. And another case is when our function f of x is equal to x, or f of x is equal to a straight line. Why is that? Because in this case, the upper side of the area is a part of a straight line, okay? So we can in principle compute the area also geometrically with using rectangles and triangles. This is the basic case, and the other case is this one, okay? You see the upper side of the area is a piece of a straight line. So here we have the sum of a rectangle and a triangle. And here we have a rectangle. If we compute the area in this way, and then we check that our results correspond to what is prescribed, what is stated by the fundamental theorem of calculus, we can, we can realize that, of course, it is correct. So, for instance, what is to compute this area, the integral between a and b of f of x dx? We don't really need the fundamental theorem of calculus in principle. Why? Because it is the area of it is the integral. It is the area between a and b of a function which is constant. Since the function is constant, the area is the area of a rectangle. So the base is b minus a, and the height is k. So it is b minus a times k. This is the area. But if you want to use the fundamental theorem of calculus, what is a primitive of our function? Our function is, for instance, f of x equal to 2. The primitive is 2x, okay? If it is equal to k, a primitive is kx. Evaluate our primitive between a and b. Kx means k times x evaluated at b minus x evaluated at a. K times b minus a, which is exactly the same. Okay? And the other example is about the other notations are just slightly longer, but take the basic case. If f of x is equal to x, x is this straight line, passes through the origin, it has a slope of 45 degrees, okay? It is the so-called identity function. So geometrically, the area between A and B of x dx is the area between the straight line and the horizontal axis, and it is the area of a rectangle plus the area of a triangle. This rectangle has a base of b, of length b minus a, and the height is a. Why is it a? Because this is the identity function. So if the abscissa is a, also the vertical coordinate is a. So the area of this part is b minus a times a, this one. What is the area of the triangle? Okay, the base is b minus a, and again, height is b minus a. So the area is b minus a times b minus a divided by 2. Okay? Now, if you expand this and this one, you can eliminate some terms, and at the end you get 1/2 b squared minus a squared. Okay? This is the result by elementary geometrical tools. If we want to exploit the fundamental theorem of calculus instead, we have to find a primitive of x, which is x squared over 2. We evaluate this at b and then at a. And we get, again, 1/2 b squared minus a squared. Okay? So these are two simple examples in which we can see immediately that we are actually computing an area, okay? In particular, this area corresponds to what we already know from high school for very simple functions. Okay. Okay. Now, we try to solve this exercise. This is another exercise on definite integrals with another type of elementary functions. Okay, so it is the integral between 0 and the log of 5 of 3 times exponential minus 1/2 x dx. So I try to find a primitive first. This is an elementary function, so 3 times exponential minus 1/2 x divided by minus 1/2, so times minus 2, plus c. So it is minus 6 exponential minus 1/2 x plus c. Now I want to point out one thing here, because I remember that last year some students got confused about this point, and also there was accordingly there were some errors in the exam, because they didn't realize that the result of this integral would be necessarily positive. Okay? Why? Because it is an area between 0 and a positive number larger than 0 of a positive function. This is a positive function. Okay, so always think about the original meaning of this, your definite integral. This is an area, and the function is above the horizontal axis, so the result must be positive. But then they got confused because they obtained this as the indefinite integral, as the primitive. But remember that what is really important to, let's say, to shape the final result of our definite integral is the value of this constant, okay? And the value of this constant will come out basically, will be specified when taking the primitive between A and B, or in general, the value of the constant, if we have the integral between 0 and an upper variable limit of integration, anyway, the value of the constant comes out later, the true value of the constant, okay? And it may be that the value of this constant is large enough to offset this negative part, okay? And to get it, and to give a positive result at the end. So don't get confused. This is just the generic expression of this. If the constant is 1000, of course, this is a positive number. Clear? Now, we have to take this primitive. This is the primitive. So we don't consider, we just put the primitive inside the operation of definite integral between 0 and the log of 5. Minus 6 is a multiplicative constant here. So we have exponential of minus 1/2 log of 5 minus exponential of 0. What is the exponential of minus 1/2 log of 5? It is the exponential of the log of 5 to the power of minus 1/2. The exponential of the log. These two operators neutralize one another. What is left is 5 to the power of minus 1/2, which is 1 over square root of 5. So this is the result. Now, look what happens here. Okay, this was negative quantity, but you have to evaluate it at the upper limit of integration, and you get 1 over square root of 5. And then at the lower limit of integration, you have to subtract minus 1. That means this is larger than this. At the end, you get a positive value, okay? 6 times 1 minus 1 over square root of 5. This is less than 1. So the final result is positive. Okay, so this is another example of the computation of a definite integral for a simple Now, compute, for instance, this is an associated example. Compute these two integrals. Integral between 0 and x, 3. Was it the same? Okay, 3 times exponential minus 1/2 t dt, and this is the first computation, and the other computation is the integral between 1 and x of 3 times exponential minus 1/2 t dt. Okay, and these are two different, by definition, two different antiderivatives, or two different primitives of this function. But they will be different in the sense that the constant, the arbitrary constant of this case, will be different from that of this case. But they will belong both to the same family. It's very easy to compute it because the first one is already part of your previous result, which was, you have to basically to put the same function here, which is the indefinite integral, into two different possible evaluations, okay? So minus 6 exponential of minus 1/2 x in this case minus 1/2 t between 0 and x, and this is the first, and for the second we have minus 6 times exponential minus 1/2 t, okay, between 1 and x. Clear? So in this case we have minus 6 that multiplies exponential of minus 1/2 x minus 1, okay, equal to 6 times 1 minus exponential minus 1/2 x. Remember that this is a positive area anyway, because our function is positive, okay? And this is the integral between 0 and x. What about the integral between 1 and x? It is minus 6 times exponential minus 1/2 x minus, so now it is 1. Okay? So it is the exponential of minus 1/2. Okay? So basically, in both cases, so it is 6 times the exponential minus 1/2 minus the exponential minus 1/2 x. So in both cases, we have both belong to the same family. 6 exponential minus 6 exponential minus 1/2 x plus a constant, okay? Both cases. But the two constants are different for the two examples. So now I hope that you understand what makes the constant different in these two examples. The fact that we start from two different points. 3. The function is like this. In one case we start from 0, and in the other case we start from 1. So the others are different, okay? We stop at x, but in the first case we start from 0, in the other case we start from 1. Clear? So basically it's clear that the constant depends on the starting point. It depends on the starting point A. In fact, if you go back to our considerations about the fundamental, the second step of the fundamental theorem of calculus, you see that the constant depends on the value of the primitive at the starting point, okay? This is in general, but we see it from the examples. Okay. I hope this is clear enough. Now we will take a break, of course, but there are more examples, not this one. And then I will show you a few more, slightly more difficult examples related to the fundamental theorem of calculus, okay? Okay, so let's take a break now. 15 minutes break. Okay, we take a 15 minutes break.